Thank you, Dr. Samet. So next we have Dr. Philip Stark, causal inference from data. A good thing.
Thanks so much for having me here. I'm actually not sure at all why I am here. I'm not from this community. I don't know anybody on the organizing committee, and I'm not quite sure why I was invited, but we'll see what I do. My best attempt to interpolate is that I'm here to channel my late mentor, one of my mentors, David Freedman. So I'm mostly talking about things extracted from from his work, which will involve being critical of some of the things that other people have said and that I expect will say. We have the next slide, please. Is that right up to me? I've got control. Okay. Is that? There we go. Okay. So what do we mean by causality? This has been addressed a little bit already. I'll talk about that briefly. When do we justify drawing causal conclusions from data? And I'm going to claim that design matters enormously in that. In fact, that's really the driving factor. Are there algorithms that can draw reliable causal inferences from observational data? And I will claim that there are no general purpose algorithms that can do that, that context matters enormously, that a lot of the machinations that people are doing with directed acyclic graphs or graphical models more generally, simultaneous equation models, et cetera, are largely ungrounded, and that what's really important is subject matter knowledge and how the data were collected, the underlying design of the experiment or the data collection. So philosophers talk about a variety of different kinds of causation. So necessary, Y doesn't happen unless X happens. X is necessary for Y to happen. Sufficient, if X happens, then Y happens. That's enough to cause it. There might be other things that would cause it as well. And then there's contributory, which I think is the general context here, that one factor alone isn't enough to make it happen. Some things have to happen in conjunction. Something contributes to it or tends to propitiate the occurrence of the consequence. And probabilistic starts to get a little bit more troubled and technical, in part because it involves thinking of reality as somehow being random. So is it the case that if X occurs, Y is more likely to occur? And what exactly do you mean by that? How do you define even what it means more likely to be, for something to be more likely to occur? And that's in contrast to a different discussion that you made earlier around probability, which is what's the probability that X causes Y? And that, I think, is an extremely philosophically troubled thing, because what do we mean by probability there at all? And I think it's a relabeling of kind of the framing of all uncertainty as probability. And that's something that I'm allergic to personally, but we'll go on. So Hume has the statement or the framing in terms of hypothetical counterfactuals that was also enunciated by the previous speaker. What we mean that X caused Y is that if X hadn't happened, Y wouldn't have happened. X happened and Y did. In some alternative universe in which X didn't happen, Y wouldn't have happened. So we want to compare two scenarios with and without the putative cause. One way to try to find those scenarios is through observational data, case control studies, some of the kinds of things that were necessary to look at smoking, because it's hard to do a randomized controlled experiment on humans with smoking, for instance. So how do you get at what would have happened but for X? And that's really the heart of the statistical question. All right. So the probabilistic version of this is, but for the fact that X happened, Y would have been less likely to happen. Again, now we're somehow framing the occurrence of Y as something that is random and that has some probability distribution, and that probability distribution is altered depending on what happened to some other variable X. That's a big epistemic leap in a lot of contexts. So It's a lot harder to think of the hypothetical counterfactual, because how do you have a hypothetical counterfactual probability distribution? Or how do you estimate what the probability distribution would have been had this not happened? You don't get that from a single observation. You need a lot of observations kind of for each case. It's a very different feel to this sort of thing. All right, so if we're thinking in terms of an exposure or some individual variable, there are a number of, and some outcome, say a binary outcome or a single variable response. There are a number of quantities that might be of interest. The first is, suppose everybody were assigned a control. Suppose nobody were exposed to this putative harmful thing. What would the average response have been? So response might be rate of cancer or something else. Second quantity of interest is, if everyone had been exposed, what would the average response have been? What would the rate have been then? And then the third quantity is derived from those two. What's the difference? So that's, in some sense, the amount of injury or the amount of response that's attributable to the exposure. And typically, this is the kind of thing that somebody's interested in estimating. All right, so the gold standard for doing this is a randomized controlled trial. And the problem in environmental exposure context is generally that's not possible, not on the menu. But I want to talk a little bit about it and then about some observational contexts that approximate that reasonably well. And then try to think about whether we can fill in the gaps when things are not that good by using more technology or not. And again, I'm going to claim that we can't. So in a randomized controlled trial, you can rigorously quantify the chance of error. You can, or for instance, that a confounder is responsible for what you see. In the taxonomy that you gave earlier of some of the things that weighed in one direction versus the other, one of the things that I would have liked to add to that plot is how well we feel we've identified the possible confounders. That was something that always comes to mind as a statistician. Okay, and then it's really important to note that random is not the same as haphazard. And we have a tendency to conflate the two. And I'll give you a metaphor because I find that metaphors are often very helpful in changing my thinking. So to take a random, suppose you want to know how salty a pot of soup is. So a very good way to do it is to take a random sample of soup, which is accomplished by stirring up the pot of soup and then taking out a tablespoon. And once you've stirred it up, it kind of doesn't matter where you take the tablespoon from. It's all going to be really, really close to the same with incredibly high probability. We're talking about probability like molecular dynamics probability. Okay. Haphazard is you walk up to the pot of soup and you stick in the spoon without looking. Okay. You can't predict what you're going to get, but it doesn't have a probability associated with it, and it's not a very good way to figure out if the soup is too salty. Okay, with randomization, the confounders tend to balance approximately, and you can quantify the extent to which they might lead to an incorrect conclusion, and you can make reliable statistical inferences. Absent randomization, we're in different levels of wishful thinking, supported in various extent by experience, by subject matter knowledge, by looking at the observational design, but it's all going to be a lot more fragile. So there is a model for causal inference in this context that was introduced by Neyman, later reintroduced by Rubin, sometimes called the Neyman-Rubin model. And this is a very helpful way to think about this stuff, that you can get a very simple cartoon that you can analyze rigorously statistically. So the idea is we have a group of subjects. The jth subject, each subject is represented by a ticket. The ticket has two numbers on it. One of the numbers on the ticket is C, which is the response that subject would have if that subject were assigned to control. And the other is T, which is the response the subject would have if the subject is assigned to treatment. Now, this can be generalized to talk about a subject is represented by a ticket with two probability distributions, a probability distribution of what the subject's response would be if assigned to the treatment group, and the probability distribution if the person were exposed to control versus treatment. Okay, so when you assign the subject to treatment or to control, that reveals exactly one of those responses. Or in the other model where we're talking about probability distributions, that reveals a realization of one or the other of those two random variables. It reveals a draw from one of the two probability distributions. The key in some of this is that the numbers on the tickets are fixed before the assignment to treatment or control. Alternatively, in the probabilistic version, the realization is independent. You can think of the random variables that represent the response are independent of the variable that assigns you to treatment or to control, and in essence are drawn before the assignment to treatment or control. So this model doesn't involve any assumption at all about the distribution of the response to control in the population or the response to treatment in the population. The only probability here is the mechanism that assigns you to treatment. There's no probability distribution or population assumptions about what the response will be in either arm. And in particular, there's no assumption that the treatment effect is the same for everybody or is additive or anything like that. It's not like smoking X years increases your chance of cancer by X, Y%, or something like that for everybody, no matter who you are. There's nothing like that going on. What is implicit in this model is a non-interference assumption, and this is really key, and it's something that holds in some contexts reasonably and not in others. Now, the idea here is that whether what my outcome is depends only on what treatment I get and not on what treatment you get. So that might be a reasonable model if we're talking about me smoking and you smoking and we don't live together. But it's not a very good model if we're talking about, for instance, communicable diseases for which there's a vaccine, where whether you get the disease might depend on whether I get the vaccine, because if I get the vaccine and don't contract the disease, I don't expose you to it. So that this interference is a serious issue in some contexts. All right. So in the Neyman model for causal inference, it's possible to make unbiased estimates of those three quantities that we were talking about before. We'll just write them down. They're very straightforward. So this script C denotes the indices of the subjects who were assigned to the control group, and T is the indices of the subjects who were assigned to treatment. Then basically the average, anyone who was assigned to treatment, we observe that individual's value of C. And the average of that value of C over the people, assigned to control. Anyone who's assigned to control, we observe the value of C for that individual, and the average for those individuals is an unbiased estimate of that first item in the bullet list before. That is the average, what the average response would be for the entire population had everybody been assigned to control. And similarly, the average response to treatment for those individuals whom we observe the treatment value of because they were assigned to treatment is an estimate, an unbiased estimate of what the average response would have been for the whole population had everyone been assigned to the treatment group. And the difference between the two is an unbiased estimate of the population difference between the two. It's the intention to treat estimate. This framework can deal with crossover of various kinds. It can't deal with deniers, but there's some things that some more complications that it can. But intention to treat is in general the most rigorous conservative analysis that you can do in a context like this. Right, so something else that you tend to see are estimates that are based on regression instead. So here's a model where the ith response, so the jth response yj is equal to some constant plus an indicator, which is 1 if subject j is assigned to the treatment group and 0 if subject j is assigned to the control group, times some parameter that is the difference between, it's sort of the boost that you get from being assigned to treatments, the difference between the response to treatment and the response to control, plus some additive noise over the number of subjects. So C is the average response to control. This is a typo. It should be the average difference between treatment and control. And then we think of the epsilons as random errors, which are generally assumed to be independent, identically distributed, and zero mean, and independent of the assignment to treatment or control. right? This doesn't match the way the randomized controlled experiment works, right? The randomness in the randomized controlled experiment is just in the assignment variable. It's not in some noise of measurement. In that model in which each individual is represented by a ticket with two numbers, there's no assumption that the difference between those two numbers is the same for every individual in the population, which is built into this through the use of delta. It's saying that the effect of treatment is additive and is the same for every subject. If you build a model like this and fit a model like this and start talking about p-values or estimates of delta, they don't correspond to the experiment. There's no reason that they should be reliable or good estimates of anything. Okay, in the context of the Neyman model, it's possible to make rigorous hypothesis tests and inferences. The easiest hypothesis to test is called the strong null, which says that subject by subject, treatment makes absolutely no difference whatsoever. All right, why is that helpful? Let me back up. So suppose that the two numbers on every ticket are, ticket by ticket, the two numbers are the same. They're not the same across tickets, but my number is the same whether I'm assigned to treatment or control. Now, if that's true, then regardless of whether you assign me to treatment or to control, you know both numbers on my ticket. So the entire probability distribution of anything that I'd like to calculate is completely specified. I know everything there is to know about the population if the strong null hypothesis is true. Everything is just determined by the randomization, and everything is revealed once you've revealed either the response to treatment or the response to control for every individual. Okay, the weak null hypothesis is that on average, and that was supposed to be a parenthetical, on average over what? Over the treated group, over the whole population, over exactly what? Treatment doesn't make any difference. So it might be that treatment harms some people and helps other people, but on average it makes no difference. That turns out to be a much harder assumption to hypothesis to test. So here's a little example. It goes back to the 1960s. It was a randomized controlled experiment on laboratory rats. It actually involved triples of siblings, but I'll talk about pairs for now. So by coin tosses, what we're going to do is assign one litter mate to an enriched environment and one litter mate to a control environment. And then after some time passes, we're going to euthanize them and weigh their brains. The treatment group was the enriched environment, and what you see kind of across the board here is that the cortical mass of the rat in the enriched environment is higher than that of the one in the control environment, with one exception. And the one exception is actually the numerical difference between the two is small compared to the other numerical differences. So this looks like pretty strong evidence that the enriched environment leads to higher cortical masses for the rats. So how are we going to analyze these data? What is a reasonable stochastic model for what's going on? How do we get a p-value or an estimate or something like that out of this? So null hypothesis going in was that treatment has no effect. The alternative was that enriching the environment increases cortical mass. So we'd probably want to do a one-sided test that would be sensitive to an increase. We're not expecting a decrease. So what might you do? Well, if you took an elementary statistics class, it might occur to you to do a two-sample student t-test. So you would take the difference between the mean for the treatment group, the mean for the control group, and divide that by some pooled estimate of the standard deviation for the difference in means. Okay. If you really paid attention in the stat class, you might think about doing a one-sample t-test on the differences, because the whole point of using litter mates was this pairing to try to control for genetic variability. And so you might look at the mean of the differences divided by the standard deviation of the differences and over whatever the normalizing factor is for student t. So this is a better idea because the litter mates are supposed to be more homogeneous, but it has very little connection to the actual experiment that was done. And you're now making strong distributional assumptions about cortical masses and other things. So a much better way to do this is to do it in a way that honors the experimental design using something like a permutation test. So we could use the same statistic, that is, the mean of the differences divided by the standard deviation of the differences, perhaps normalized. But the way we find the way we figure out whether the value of that statistic is surprising or not isn't by reference to students' t-distribution, because nothing is going on here that connects it to students' t-distribution. Instead, we could figure out the distribution of that statistic based on the actual randomization that occurred. So what the actual randomization that occurred, if the strong null hypothesis is true, oh gosh, I'm having formatting errors in this. 211 should be 2 to the 11th. So if the treatment has no effect whatsoever, then it doesn't matter which of the two siblings was assigned to treatment and which was assigned to control. They're going to have the same cortical masses either way. And all that changes is the sign of the difference. The difference, the values would be the same, the difference would be the same, but the sign would be different depending on which rat was in treatment and which was in control. And so we'd have 2 to the 11th different possible data sets that could have arisen from this experiment, corresponding to just flipping the signs of these things. And it's like a coin toss as to whether 32 has a plus sign or a minus sign attached to it in this thing. Okay. So, all right. What are some of the alternatives that we might think about? It could be that there's a shift, that is, that you add the same amount to the mass of the cortex, or a scale, you multiply it by some constant, depending on whether it's treated or not. There's concern about interactions and interference. In this case, the littermates, I think, were isolated from each other, so there's no issue there. Right, so if we applied these tests, what are the assumptions that we're making tacitly or otherwise in coming up with a p-value? For the two-sample t-test, we're assuming, if we interpret that using tabulated values of the t-statistic, critical values of the t-statistic, we're assuming that the masses are an independent, identically distributed sample from a normal distribution, that we're drawing the masses of the cortices of the rats that were assigned to treatment from some large population that has a normal distribution of masses, that has an unknown variance and some mean, and we're drawing the masses of the brains of the rats in the control group from another normal distribution that has the same unknown variance as the one that the treatment group was from, and has the same unknown mean. Okay, that's the assumption. That has nothing to do with what happened, right? It's just, okay. It does test the weak null hypothesis, that is that on average there's a difference rather than sub-pair by sub-pair there's a difference. And also built into it are the assumption of normality, independence, non-interference, so forth and so on. The one-sample t-test makes slightly fewer assumptions in that it's not assuming that the two different sets of masses are drawn from normal distributions with the same variance and the same unknown mean, but rather that the differences are drawn from a normal distribution with mean 0 and unknown variance. So again, there's no reason for that in anything that was done. There's no reason for that to be true. In contrast, in the permutation test, really, it's the assumptions, the probabilistic assumption of the test is true by fiat. It's true because a coin toss was used to decide which sibling got which treatment. It does still assume the non-interference, but other than that, it's really distribution free in that sense. So if you do the calculations, the student t for the one-sided paired t-test gives you a p-value of 0.0044, which is quite strong evidence. But again, it's evidence that the null hypothesis is false, but the null hypothesis includes assumptions that we have no reason to believe are true in the first place and find kind of questionable, like normal distributions of cortical masses and sampling from some larger population. Okay, all right. The in contrast, if you use the same statistic, the t-statistic, but you calibrate it using the permutation distribution, you get a p-value of 0.0011. It's an even smaller p-value, so even stronger evidence against the null hypothesis, and it's evidence against a null hypothesis that's more relevant, right? It's one that actually, where the probabilistic aspect of it is coming from the design rather than coming from some assumption about distributions in populations. How am I on time? I'm all right? All right. How much? 15? Okay, I'm probably go ahead then. All right, so in fact, this experiment had triples, not pairs. It had an impoverished environment, a normal environment, an enriched environment, and you can think about analyzing the data in an analogous way where every one of the 3 factorial assignments of the littermates to one of the 3 treatments is equally likely. And analyzing the data that way, again, makes a lot more sense than, say, using an F-test, which might be the natural thing that would occur to someone to do, because the assumptions of the F-test are a lot harder to justify, and rejecting on the basis of the F-test could be rejecting because some of those stochastic assumptions are wrong, not because the hypothesis as we informally state it, that is, treatment makes no difference, is wrong. So the assumptions involve, again, samples, IID samples from normal distributions, so forth and so on. All right, regression with dummy variables is another way people might think about doing that, but there's again, it's a stretch. All right. These did not format that well. Okay, so we all know that association isn't causation, even if it's really, really strong association. Most of the techniques that try to extract causal relationships or draw causal inferences, especially from observational data, amount to still using association as a proxy for causation, perhaps with some additional structural assumptions about the underlying problem. So this brings us to a very important theorem. It's Freedman's rabbit hat theorem, which says to pull a rabbit out of a hat, at least one rabbit must first be placed in the hat. Okay. So I usually derive this from the rabbit axioms, which says for the number of rabbits in a closed system to increase, the system must contain at least 2 rabbits, and there's no such thing as a negative rabbit. So that lets you derive a corollary, which is you can't pull a rabbit out of a hat, out of an empty hat, even with a binding promise to return the rabbit later. So if you make assumptions and draw a causal inference on the basis of those assumptions, or draw a conclusion on the basis of those assumptions, and that your conclusion somehow passes the test of randomness or passes the test of causation, it doesn't justify what you did. You can't bootstrap yourself in that particular way. All right, so the methods that are generally used to try to draw causal inferences from observational data put the rabbit in the hat in some form or another in terms of assumptions that often aren't made terribly explicit or that are difficult to follow. So here's an incomplete listing of some of the methods that people use to draw conclusions from observational data: regression, path models, simultaneous equation models, directed acyclic graphs, tetrad, which Professor Schein's worked on. Okay, this didn't render correctly, but there are supposed to be arrows among these things, including an arrow that, an arrow from here to here, from here to here, from there to here, and then from here back to there. So that graph has a cycle. It's not of the form that people prefer to use for causal inference because we have things sort of mutually influencing each other as opposed to something else. This is an example of a directed acyclic graph. The way that these things are interpreted in context is that arrows kind of denote dependencies, and so C depends on A and B, but E is conditionally independent of A and B given the value of C. So if you, the sort of direct causal effects are represented by arrows. There's some actually deep mathematical theory saying that for models like this that are directed acyclic graphs, if you're interpreting them as probability distributions, then you can, there's a Markov condition that, that really, that says that you basically can represent these things as, E is conditionally independent of A and B given C, and that under faithfulness assumption, you can reconstruct the arrows, which arrows are present and which arrows are absent, if you know the joint probability distributions of these things. So if you can test whether E is, conditionally independent of A and B given C, then you could determine which arrows are there and which are not. There's a difficulty in that assumption involves a number of things. So the probability distributions that needs to hold for all values of the parameters in the distribution, and it involves knowing the distribution exactly rather than estimating the distribution from data. You need to know that things are exactly conditionally independent of each other, have exactly no association in the Gaussian case. And that's essentially impossible to do from data. If you, in addition, add the assumption that arrows don't just represent dependence, they represent causality, then you can infer causality. But that's an assumption about how the world works. It's not something that comes from the data in any particular problem. So the subject matter knowledge is somehow inextricably linked here. You need to know that you've identified every potential confounder, everything that feeds into each of these things is on the menu. And if not, you're still subject to the possibility of confounding and making and drawing erroneous conclusions. Okay. All right. So forgive me. I'm going to cast some shade here, but the approach that they've taken, in essence, redefines causality to be arrows in these graphs. It does involve the Markov condition, the faithfulness assumption, causal Markov condition, and the assumption that sort of approximate sample independence is exact population independence. And that's a lot of assumptions. Okay. If you're trying to draw causal conclusions from regression, including all of its variants, logistic regression, et cetera, you have also comparably strong assumptions about how the world works in your particular problem for your particular data. In essence, you're assuming that the functional form of your regression model is a response schedule, that it describes it's not just a summary of the data that you've observed, it describes how nature generated the data in the first place. It involves stochastic assumptions about noises, about realizations of random variables. I'll give you an example that came up in a very different context. This was in litigation. Actually, you know what? I'm going to skip that. Forgive me. All right. Other places where I see issues in the foundations of statistics coming into play in causal inference. One is we tend to conflate rates with probabilities. So anytime we see a rate, we tend to think of it as a probability or as the result of a probability. So to give an example, if I were to say that in the next year, one person in this room will die, what's the chance it's you? We're somehow invited to think that it's 1 over the number of people in this room. Whereas if I say that there's n people in the room, one of them is named Philip, what's the chance that it's you? You're not invited to say 1 over n. And somehow ignorance gets conflated with probability. If something is the result of random trials, it will lead to a rate. But the fact that you've observed a rate does not mean that it's the result of anything random. And that's something to just keep in mind. In things like logit and probit models, what does the probability even mean? Why is the thing generated by a random mechanism? Okay. And then, describing a data set is not the same thing as predicting what the next observation will be, and neither of those is anywhere near as hard as predicting what the response would be to an intervention. And that's really what we're after for causal inference. Okay, in a legal setting, people talk about general causation. Is A capable of causing B, or is A known to cause B under some circumstances? And then specific causation. I was exposed to A, and B happened to me. Is A the actual cause of B for me? Specifically, did it cause my injury? There's a standard that's used in court, and this seems to be connected to something that you spoke about. I think was it Mills or Hill was the looking at this population attributable risk. Is that I think it's related to this. So in the law, there's come to be a standard that says if the rate of illness or injury in the exposed group compared to the rate in the unexposed group is bigger by a factor of 2 or more, then you conclude that my particular exposure caused my particular injury. It turns out that even if you grant general causation, that A can in principle cause B, so forth and so on, the average probability that illness was caused by exposure, given illness and exposure, isn't necessarily the relative risk. It can be as small as the difference between the risks in the two groups. So if I have something that occurs at a rate of 3% in the exposed group and a rate of 1% in the unexposed group, it doesn't mean that more likely than not an individual in the exposed group who has the illness, that their illness was caused by the exposure. In fact, the probability that their illness was caused by the exposure could be as little as 2%, the difference between 3 and 1. Right? This is just the math. So it turns out that heuristic is kind of ill-founded. All right, so an example of an observational study that really gives a basis for very strong causal inferences is Snow's study of how cholera is communicated. So for those not familiar with his work, this happened before the germ theory of disease was promulgated. There were arguments over what caused cholera. There were epidemiologists claiming that it was caused by miasma, bad air, and in fact fit models to things like elevation away from the Thames River and related the height to the frequency of occurrence of cholera. So Snow identified the index case in a cholera outbreak that happened, I think, in 1848, and then which was a sailor arrived, slept in some bed. He got cholera. The next person to sleep in the bed also got cholera, and that was fairly compelling evidence. But what really kind of settled this, I think, was looking at what happened after 1854. He mapped the residences of victims. They concentrated near a particular public water pump. There were a few buildings in the area that were relatively unaffected. It turned out that their water suppliers were different. He showed that most of the victims in other parts of London had drunk from that particular pump. The water suppliers in different buildings, there was a time when water suppliers were competing for business, and it could be that one building was right next to another building that were supplied by different suppliers. So there was very good. It was a very good natural experiment where, first of all, it was blind. People didn't generally know who their water supplier was. Secondly, it was mixed across socioeconomic status, everything that you could possibly imagine. The things that were different among these households really was the water supply and very little else. Between the earlier cholera epidemics and the epidemic of 1853-54, one of the water suppliers actually moved its intake further upstream in the Thames River, so to a place where it didn't contain the sewage and other effluent from the city. So he imagined that on the basis of that, there should be a diminution in the rate of cholera, and it should be concentrated among those people who were supplied by that water supplier. And indeed, he mapped it out. I mean, this is an enormous amount of shoe leather expended in trying to figure out what's going on. And I'll take 3 of my remaining 5 minutes to read this. So this is from Snow. Although the above facts shown in the table above afford very strong evidence of the powerful influence which the drinking of water containing the sewage of a town exerts over the spread of cholera when that disease is present, yet the question does not end here, for the intermixing of the water supply of the Southwark and Vauxhall, I don't know how to pronounce these words, company and that of the Lambeth company over an extensive part of London admitted the subject being sifted in such a way as to yield the most incontrovertible proof on one side or the other. In the sub-districts enumerated in the above table as being supplied by both companies, the mixing is of the most intimate kind. Pipes go down all the streets, into all the courts and alleys, et cetera. Few by one company, a few by another, according to the decision of the owner-occupant when the water companies were in competition. Rich and poor, large houses and small, no difference in condition or occupation of the persons receiving the water. So he's really worrying very hard about confounding, right? And really seeing that that what happened naturally was very, very close to a randomized experiment. Okay, so let's go to the table. 300,000 people of both sexes, every age and occupation, every rank and station, gentle folks to the very poor, et cetera. Okay, so this is what he found. If you look at the deaths from cholera for the water supplier that had moved its intake upstream, the rate per 10,000 was far, far smaller than it was from the ones that were taking in the water from downstream. And this decrease for the rest of London was somehow in between a little bit. But this was very, very compelling evidence, especially when you compare it to what had happened in the previous epidemic when things were not spread. All right, so conclusion, observational studies, confounding is the rule, not the exception. Reliable causal inference requires good experimental design or an observational study that's tantamount to an experiment. You ought to analyze your experiments with methods that honor the actual design, not just throwing statistical technology at them. I'm arguing, but haven't shown, that sophisticated analyses can't compensate for bad design. I think it's better to think of algorithmic results as conjectures to be verified rather than as proof of anything. To pull a rabbit out of a hat, you have to put at least one rabbit in the hat first. And so the moral is guess but verify. So use whatever technology you want to generate your hypotheses, but when it comes time to test them, you need to worry a lot harder. So thanks a lot.